Okay, here's yet another question focusing around differentials and that drag force. The difference here is that this is actually part D of the problem, where parts A, B, and C have to do with conservation of energy. And this is only just part of the picture. I just put it up here so to help us with our free body diagram, because if you know here on the problem, they don't ask for the free body diagram. Okay. So we've got this block being released from the top of an incline, reaches a horizontal surface, moving at a speed v0. The block experiences so we're looking at this point right down here, okay? And the block's going to be moving to the right with a mass of v0 once it encounters that horizontal surface. Now suppose the block is going to experience a resistive force as it slides on the horizontal surface. The magnitude of the resistive force is given as a function of speed of F equals beta v squared, okay? Where beta is a positive constant with the units of kilograms per meter. The next, so part one of it says write but do not solve a differential for the speed of the block on the horizontal surface as a function of time before it reaches the spring. Express your answer in terms of m, h, k, beta, v, and physical constants as appropriate. And then using the differential equation from part D, I, right? So the first part of D, show that the speed of the block v of t as a function of time can be written in the form of 1 over v of t equals 1 over v0 plus beta t over m. So they actually give you your result, okay, your answer. And so what you need to do is you need to prove it or show that you get to that point, right? So the points are not, so I can tell you for that second part, it's not going to be a, the answer itself is not going to be an actual point, okay? And so let me just bring something up. There we go. All right, and so for our free body diagram, while it's on the horizontal surface, right, we're going to have Fn, Fg, right, our standard, and then it's going to have this F drag, or F they're calling it. Remember, when it's just sliding, it has no applied force to the right, so the only force in the horizontal direction is to the left, okay? So part I, right, so D, part I, is going to be, we're going to sum the forces, so we're going to say negative F equals MA, right? Because that's the only force exerted in the horizontal direction, but they tell us that F has a value of beta v squared, right? And so now we're going to plug in our dv dt to replace our acceleration, okay? This is really the answer, right? Because remember, this right here is our differential, and that's what they mean by a differential equation, okay? Don't go splitting that yet, because that's not what they're looking for here. The only other thing you would probably get credit for is if you divided that m over, right? So this would be another version where you would get points for. But that's neither here nor there. I mean, that's just really setting up your solving for the next one, okay? But you could stop, excuse me, after you get to that negative beta v squared equals mdv dt, okay? Now we're going to go to part 2, right, which is to now solve our differential, right, and show that our velocity function ends up looking like 1 over v of t equals 1 over v0 plus beta t over m, right? So so beta v squared equals m dv dt, okay? And so remember, get v's to one side, everything else to the other side. So I'm going to multiply with this by dt over m, right? And so it's going to be beta v squared over m dt, right, equals dv. And now I'm going to divide both sides by v squared. All right, so it's going to cancel there, pop up over here. And so I'm going to get beta over m dt equals 1 over v squared dv. And now this is the point we have our variables separated, right? We split apart that dv dt, and we have them on opposite sides of our equation. So now we can take our integrals. Oh, sorry, I mismarked the integral in that second part. Okay, and so you are going to get beta t over m, right, plus c. Now, the common thing here is to, because you see that 1 over v, sometimes students will make the mistake and say, okay, that's just the natural log. But you have to remember, the natural log only applies when it's 1 over anything to the first. So I can rewrite 1 over v squared as v to the negative 2 dv, which then when I follow my rules, I end up with v to the negative 1, not negative 2. So I write a 2 there. So over negative 1, right? And so really this just becomes 1 over, right? So this becomes negative 1 over v, right? And so there's our function. And so now you can see why you get they want this look right here, okay? Now where the rest of it comes from, they do tell you that the function is equal to v0 when t equals 0, okay? So you can figure out what c is right now. And so let me give myself a little bit more space. All right, so I'm going to plug in that when t equals 0, all right, v is v0, right? Okay, and so I feel like I'm missing a negative sign somewhere. Oh, I am, because this was negative, right? Because it's negative bv squared, or beta v squared, okay? And so that still doesn't seem like I'm missing something. I'm missing another negative sign somewhere. That becomes negative, beta, right? This is negative. Because c should be, okay, I got it. I know what we're gonna do. So this ends up being 0. So c equals negative 1 over v0, which here's that signature right there, right? And so now when I plug it in, I'm going to get negative beta t over m minus 1 over v0, because that's now my c, equals negative 1 over v. There's where my extra negative sign, since they're all negative, right? I can get rid of that negative sign and make everything, or I can multiply this by negative 1, which turns everything positive. So 1 over v of t equals beta t over m plus 1 over v0. And that was the answer that they're looking for, okay? Again, this was part of a question, so you could see that pop up as well on the test.